Welcome to MSP lecture series on main group chemistry. In my previous lecture, I was discussing about the chemistry of group 13 elements. While discussing the chemistry of boron hydrates, I had mentioned that I would give more details about Wade's rules to explain structure and geometry of boron hydrates. Today let me do that one. So, let us consider the utility of Wade's rule in explaining structures of boron hydrates. The bonding in boron hydrates and also polyhedral borohydrate ions essentially involve conventional 2 center 2 electron bonds, that is normal. So, every bond requires 2 electrons along with 3 center 2 electron bonds. Okay. Since group 13 elements are in particular boron being for having S2p1 electronic configuration. Okay. In order to have a stable tetrahedral geometry with coordination number 4, they are in short of 2 electrons. So, they are electron deficient, and most of the electron deficient molecules tend to have some bonds similar to 3 center 2 electron bonds. So, boron cluster compounds essentially utilize delocalized molecular orbitals containing these electrons that contribute to the stability of the entire molecule. Okay. So, I repeat again, boron cluster compounds essentially utilize delocalized molecular orbitals containing electrons that contribute to the stability of the entire molecule. So, after setting aside the number of electrons that are required to make 2 center 2 electron bond, remaining electrons are essentially utilized in building the cluster involving 3 center 2 electron bonds depending upon how many hydrogen atoms are there that are going to bridge to boron atoms. Okay. So, in more complex boranes, okay, 3 center 2 electron bonds may lead to a BHP bond, as I had mentioned, or 3 boron atoms lie at the corners of an equilateral triangle with their sp3 hybrid orbitals overlapping at its center. So, let me show you that one in this diagram. You can see here, let us say each boron atom is having one sp3 empty sp3 orbital, okay, and 2 others have 1 electron each. So, they overlap in this fashion to have a bonding of this type. Okay. This is also essentially 3 center 2 electron bond. So, let us look into more details about Wade's rules. So, electron deficient species possess less number of valence electrons, as I had mentioned, than are required for localized bonds. So, in a cluster atoms form a cage like structure. So, there are a great number of known neutral and anionic hydroboron clusters. The structures of these clusters are often described as being polyhedral or deltahedral. A deltahedron is a polyhedron that possesses only triangular faces. Triangular means equilateral triangles. For example, let us consider octahedron. Okay. If you take octahedron, so if you just look into this one, it is one face made up of equilateral triangle. We have 4 such triangles here, 4 such triangles here, that is the reason it is called octahedron. So, this is one of the example for deltahedron. I would give you more details about other deltahedron. Okay. So, for example, you consider here B5H5, we have 5 vertices are there occupied by boron atoms, and in similarly if you look into B6H6 2 minus. So, we have 6 boron atoms occupying 6 vertices of a regular octahedron. Similarly, here we have B5H9. So, one of the axial position of octahedron is missing. So, and then we have this one B12H12 2 minus. Here in this case the structure is called icosahedron. Okay. I will show you these structures later, and also similarly we have B5H11, and also we have some prefix here closo 1 2 B4 C2 H6, it is a carborane. What is this closo is all about? I will be elaborating when I start discussing on Wade's rules again. Okay. So, Professor Kenneth Wade's proposed this theory to explain bonding in boron hydrates and similar type of clusters of main group elements as well as metal carbonyls. And here you can see earlier when you are looking into the structure of diborane, that is B2H6, we proposed this kind of 3 center 2 electron bonds where filled sp3 of boron interacts with 1s1 electron of hydrogen with an empty sp3 of another boron to form 3 center 2 electron bonds like this, and of course, here if you look into terminal 1 they are conventional 2 center 2 electron bonds. Now, let us look into the types again, the type of boron hydrates we have. We have two series, one is BnHn plus 4 and another one is BnHn plus 6 series, and some examples I have given here in case of BnHn plus 4. So, B2H6, B5H9, B6H10, B8H12, B10H14, and similarly in this series we have B4H10. So, essentially by just counting the number of boron atoms and hydrogen atom, you should be able to tell whether it belongs to BnHn plus 6 or BnHn plus 4 series. So, some examples is shown here. So, B4H10 belongs to BnHn plus 6 series, and this one B5H9 belongs to BnHn plus 4 series. Now, let us look into the Wade's rules. First, what we should do is determine the total number of valence electrons present in a particular boron hydride. So, for example, we know that boron has S2P1 electronic configuration. So, we have 2S2 2P1. So, totally we have 3 electrons in its valence shell. Similarly, hydrogen 1s1, we have 1 electron is there. So, that means each boron will give 3 electrons and one hydrogen will give 1 electron. So, in this way what we should do is in a given boron hydride we have to count total number of valence electrons that are coming from boron as well as hydrogen. Okay. Add or subtract electrons for any overall charge. If positive charge is there, subtract 1, or if negative charge is there, you add 1, depending upon how many charges are there. And now, after counting and totaling all the valence electrons coming from boron as well as hydrogen, we have to subtract 2 electrons for each BH bond. For example, if we have say Bn boron hydride, so NBH terminal bonds will be there. So, in a Bn polyhydride, we will be having NBH bonds. They are essentially they involve 2 electrons. So, it is a BH bond. Okay. So, that means, so after determining, just subtract 2 electrons for each BH unit or CH unit if it is a carborane. The number of electrons, remaining electrons, if you divide by 2, we get a number that is called SEP. Okay, this is called skeletal electron pair. So, you can see here I have given these details. So, a cluster with n vertices occupied by n boron atoms requires n plus 1 skeletal electron pairs for bonding. Such clusters are called closo. Example, octahedron will require 7 skeletal electron pairs and icosahedron would require 13 skeletal electron pairs. In case of octahedron, we have 6 vertices are there. So, we need n plus 1 means 7 skeletal electron pairs. If you look into icosahedron, we have we have 12 vertices are there. So, here 12 plus 1 that is 13 skeletal electron pairs are required. Okay. So, this is how one should be able to decide the type of cluster. If there are n plus 1 skeletal electron pairs are there. So, that means for closure, so n vertices and n plus 1 skeletal electron pairs. Okay. And for example, if we have n plus 1 skeletal electron pairs and n minus 1 boron atoms. Okay. So, this is n vertices means essentially n boron atoms. Okay. And then in case if we have n plus 1 skeletal electron pair and we have n minus 1 boron atoms. So, then it is called nido. Similarly, if we have n plus 1 skeletal electron pairs and we have n minus 2 boron atoms, okay, that is called arachno. Okay. So, this is how we can classify boron hydrates clusters. If there are more than Nb atoms and n plus 1 skeletal electron pair, the extra boron atom occupy capping position over triangular faces. You should remember, if there are more than Nb atoms and n plus 1 skeleton pairs, the extra boron atoms occupy capping positions over triangular faces. Okay. For example, octahedron is there, it becomes capped octahedron. So, Wade's rules can also be applied to a wide range of other clusters of main group as well as transition metals, that I would discuss later. Okay. Okay. So, let us look into the type of clusters whatever I showed here. So, closo, okay, n plus 1 skeletal electron pairs will be there and then n number of vertices or n boron atoms will be there. So, in here when we have n plus 2 skeletal electron pairs are there or n plus 1 skeletal electron pairs are there, n minus 1 boron atoms will be there, that is nido. Similarly, n minus 2 boron atoms will be arachno, and if we have n minus 3 boron atoms, that is called hypo. So, we do not have any example among boron hydrates for hypo type structures. Okay. So, I was telling about deltahedra. So, deltahedral cages with 5 to 12 vertices are the parent cages used in conjunction with Wade's rule. Wade's rules to rationalize boron cluster structures. Boron cluster structures, as a general rule, when removing the vertices from these cages to generate nido framework, remove a vertex connectivity 3 from the trigonal bipyramid. So, for example, let us look into a trigonal bipyramid. So, this is a typical trigonal bipyramid. Okay. So, for example, this has now, if you just look into it, you have 1, 2, 3, 4, 5 vertices are there, and from this one if we have to generate a nido structure, we have to take out the vertices that makes 3 connections here, 1, 2, 3 connections, either this one or this one can be taken out. This makes 4 connections, this should not be taken out. So, just take out this, if you take out this one, it would be something like this. So, we will get a tetrahedral structure. So, this is a nido. Okay. So, this is how it is, and similarly one cap from the octahedron or icosahedron, a cap from this one, we have to take out this cap. So, this one we have to take out, it becomes square pyramidal. For example, if we take out this one, it becomes like this. Or in case of icosahedron, okay, you have to take out one of the caps here. Okay. In this one we have 5 here, 5 here, and 10, 11, 12 is there. So, you have to take out one. Okay. And of course, from square antiprism, this is square antiprism. Okay. So, this square antiprism is this one. This is a square antiprism. Basically, a cube, if you just turn it and make it staggered one of the face, it becomes, and then connect them with triangular faces, it becomes square antiprism. And this one, if we put here one more vertices, okay, it will be monocapped one. If I put one more here, it is bicapped one. So, it is something like this. So, something like this. This is monocapped one. Similarly, I can put here, it becomes bicapped square antiprism, and from this one you have to take out this. for 8. Okay. For 9 also you can take out 1, for 8 you have to take out both of them. Okay. Okay. So, here again I am showing you the details. Clozo will have n plus 1 electron pairs, skeletal electron pairs, and nido would have n plus 2 skeletal electron pairs, and arachno will have n plus 3 skeletal electron pairs, or if you have n plus 1 skeletal electron pairs, you have n minus 2 boron atoms in case of arachno, or if you have n plus 1 skeletal electron pairs and n minus 1 boron atoms, that is nido, or if you have n plus 1 skeletal electron pairs and n boron atoms, that is called clozo, and hypo and clado are rare, where you have n minus 3 boron atoms for n plus 1 skeletal electron pairs and n minus 4 boron atoms for n plus 1 skeletal electron pairs are essentially called as hypo and clado. They are rare. We do not have any examples among boron hydrates for these two cases. Okay. So, essentially some of these terms are coming from Greek or Latin. Clozo comes from Greek for cage, nido the Latin for nest, and arachno in Greek for spider, hypo Greek for net again, and clado the Greek for branch. So, this is how the prefix have been included to different type of boron hydrate clusters. Okay. So, I have shown here with n equals 5, this is trigonal bipyramidal. So, n equals 5, this is trigonal bipyramidal, and n equals 6, this is octahedron. So, this is octahedron. N equals 7, of course, you can imagine pentagonal bipyramidal. N equals 8, dodecahedron. It is very simple to imagine dodecahedron. Okay. So, this will give rise to a dodecahedron. So, this is a trigonal prism, this is another trigonal prism. Connect them this way, not this way. If you connect this way, and if you see, this will have 2, 4, 6 plus 2, 8 vertices are there. So, n equals 1, 2, 3, 4, 5, 6, 7, 8. This is dodecahedron. And what we have next is tricapped trigonal prism. Okay. For trigonal prism, you can take this is a trigonal prism. You start capping these positions here. You put 1, connect 4, and similarly here is monocapped, his bicapped, and here it is tricapped. Okay. We can take like this here. Okay. And we can connect this way here. Okay. Something like this. Okay. So, it is monocapped. Okay. And similarly, I can put one more here, it is bicapped, and if I put one here, tricapped. This is for n equals 9, this is the symmetric polyhedron for vertices if 9. If 9 boron atoms are there, this is the structure for clozo. Okay. And similarly, bicapped square antiprism. Bicapped square antiprism, as I mentioned, we can take this one. Okay. And if I put one more here, so this is now, if you see here, monocapped, bicapped. This is bicapped square antiprism. Okay. And also we have next one is for n equals 11, octadecahedron, and then for 12 it is icosahedron. I showed you this is icosahedron. We have 5 here and another 5 here, and then 1, 10, 11 and 12. We have 12 vertices. This is icosahedron. Of course, you can see deltahedron. This is a monocapped, this is bicapped, and this is tricapped. A deltahedron is plural, is a polyhedron whose faces are all equilateral triangles. If you just look into it, they are all equilateral triangles, and all faces should be equilateral triangles. And let us now predict the structures of some boron clusters using Wade's rules. Now, let us predict the structure of, let me look into a problem. Okay, if you learn chemistry through problem, chemistry is not a problem. So, predict the structure of B5H11. As I had mentioned, we should start counting the electrons from boron and hydrogen. We have 5 boron atoms are there. So, 5 into each one will give 3 electron, S2P1, only we have to count only valence shell electrons. So, each boron has 3 valence electrons, 3 into 5, plus we have 11 hydrogen atoms. So, 11 into 1. So, totally we have 15 plus 11, 26 electrons are there. Out of 26 electrons, we have to subtract 2 electrons per boron atom to make a BH bond. So, we have here in this case, we have at least minimum of 5 BH bonds, and each one will require 2 electrons. So, we should take 10 electrons from this one, okay, and then remaining electrons will be utilized in cluster building. So, we have about 16 electrons here, okay, and 16 electrons divided by 2. So, here it is 8 skeletal electron pairs, okay. 8 is the this is essentially equal to n plus 1 if you consider closo, okay. If it is n plus 1 equals 8, so n equals 7 should be closo. So, and then if n plus 1 equals 8, n equals 6, it is nido. If n plus 1 equals 8, n equals 5, it is arachno, okay. So, now we have only 5 boron atoms, that means essentially n minus 2 boron atoms are there. So, as a result, this is arachno structure. So, arachno structure should be derived from the closo. Closo means here vertices should be 7. For vertices 7, polyhedron we can consider is pentagonal bipyramidal. From pentagonal bipyramidal, what we should do is we have to take out 2 vertices, okay. So, let me show you how we can arrive at the structure. See, now we are taking a pentagonal bipyramidal here, because the closo for that one is vertices are 7 vertices, okay. And from this one we have to take out 2 vertices, okay, and this is the closo structure. This would have been ideal if we had 7 boron atoms. So, we do not have 7 boron atoms, we have now 5 boron atoms. So, we have to choose which one has to be taken. So, these 2 has to be taken out, okay. First one from the capping one, and next one from the plane. So, this has to be taken out. Once if you take out this one, this is the skeleton we will be left with 5 boron atoms. This represents the skeleton of B5H11, and now we put all the hydrogen atoms. This is how it looks like. So, this is the structure of B5H11 predicted using Wade's rules, okay. I hope you have understood this one. Let me do more examples to make it clear. Now, I have 3 more problems here. The first one, look into it. Rationalize why B6H62 minus adopts an octahedral cage. So, here we should prove that B6H62 minus has octahedral geometry, and similarly B12H12 2 minus has icosahedral structure, and another one is B10H10 2 minus that shows bicapped square antiprism. Okay. So, let us look into these 3 problems one at a time to make you familiar with Wade's rules. Okay. Let me start with B6H6. Let us start counting the electrons in B6H6. So, 6 boron atoms are there. So, each one is giving C. As a result, 6 into 3 and plus 6 hydrogen atoms are there. Each one will give 1, plus 2 charges are there, negative, should be added. So, what we have is 18 plus 6 plus 2. So, that means essentially 18 plus 6, 24 plus 2, 26. electrons are there. Out of 26 electrons, okay, we have at least 6 BH bonds. So, 6 BH bond would require, okay, each one requires 2 electrons. So, it requires 6 into 2 equal 12 electrons. So, remove 12 electrons from here minus, okay, minus 12, okay. So, it will give you 14 electron. So, 14 electron divided by 2 will be 7 skeletal electron pair, and this is a n plus 1. Okay. If it is n plus 1, so we should have n boron atoms. Okay. So, if you have n boron atoms, this is called closo. So, since we have 6 boron atoms are there, so it is a, so B6H6 2 minus has closo structure. So, it has a closo structure, that means it is something like this, and in this one what we have is each one has one BH bond. It is something like this, okay. One can add. So, here we can add here. So, this is your BH bond, so that this is the structure of B6H6 2 minus. Okay. We should put 1 2 3 here, 1 2 3 here. So, we have B6H6 2 minus. Similarly, let me look into B12H12 2 minus. Okay. So, B12H12 2 minus. So, 12 into 3 plus 12 plus 2 charge. So, 12 into 3 is 36 plus 12 plus 2. Okay. So, total we have 50 electrons are there. Yeah, 50 electrons are there. Out of 50, what we need is we have to deduct 24 electrons for 12 BH bond. Okay. So, 12 into 2 equals 24. Okay. So, then we have 26 electrons are there. This will be 13 skeletal electron pairs. This is n plus 1. Okay. So, in order to have a closo structure, we should have n boron atoms. N boron atoms, okay, will give a closo structure. So, we have n boron atoms, 12 boron atoms are there. Okay. So, that means the structure is icosahedron. So, structure will be something icosahedron, and at each vertices a boron atom sits, and each boron makes a BH bond. So, this is how we can explain. So, about B10H10, 2 minus. In the same fashion, we can count each boron is giving 3 electrons, to 10 into 3, and plus here 10 into 1, okay, and plus charge. So, here 30 plus 10 40 plus 2. So, 42 electrons are there. Out of 42 electrons, we have to deduct for 10 BH bonds 20 electrons, 10 into 2. So, remaining 22 electrons are there. If 22 electrons are there, it will be 11 skeletal electron pairs. This will be n plus 1. Okay. So, then if we have n boron atoms, this will be closo. So, we have n boron atoms, we have n is 10. So, this has a closo structure, and this closo structure will be having bicapped anti-square prismatic geometry. So, you can see here, I can say here bicapped square anti-prismatic geometry. So, you can see here, this is the one. Okay. So, this is one, you can see here. So, 4 here and 4 here, okay, 8, 9 and 10. So, this is bicapped anti-square prismatic for B10H10 2 minus. So, this is how we can derive the structures usually for neutral or anionic boron hydrate. So, in my next lecture, I will be giving more details and also application of Wade's rule to other main group clusters. So thank you very much and have a very pleasant reading of inorganic chemistry and understanding of Wade's rules.